We present S2O, Static to Openable Enhancement for Articulated 3D Objects. Recent work has contributed large and diverse datasets of static 3D environments. However, there is an increasing need for interactive environments for embodied AI. While many common interactions involve articulated objects like fridges, the available datasets of such articulated 3D objects are limited in scale and diversity. As the objects that could be articulated in such datasets are mostly openable, we formulate the S2O task. Our goal is to enhance existing static 3D objects into articulated 3D objects, that can be used to create interactive environments at scale. To this end, we propose the static to openable task. That is, given a static mesh as an input, produce an articulated version of it as an output. We specifically concentrate on openable containers with drawers, doors, and lids. Starting with static 3D mesh, we can use it either directly or leverage intermediate representations such as RGBD images or point clouds. The first step of our pipeline is part segmentation, where we detect and segment all openable parts. The second step is motion prediction, where articulation parameters for all openable parts are computed. The last step of our pipeline is interior completion, where we create the interior geometry of openable parts such as drawers, that is typically missing from static 3D meshes. After the initial benchmarking of state-of-the-art methods across different modalities, we find that point cloud-based methods work the best. We propose FPN group, building on top of point group. The next step of our pipeline is motion prediction. Here we can compare representative approaches from prior work. We propose FPN group mode, as well as simple yet effective heuristic-based approach. In the last step, we complete the interior geometry of the openable parts. We specifically concentrate on drawer interior completion and propose a heuristic approach that performs surprisingly well. The final output of our static to openable pipeline is an articulated 3D mesh, with segmented openable parts, corresponding motion parameters, and completed interiors of drawers. To enable systematic benchmarking on our task, we created two datasets. We call the first PM Openable, as it is based on the annotated 3D object articulations from the PartNet Mobility dataset, one of the few such datasets contributed by prior work. Unfortunately, we observed that this dataset exhibits limited diversity in articulated objects and high similarity between training, validation, and test splits. Therefore, we curated another dataset, which we call the Articulated Containers dataset, ACD. This dataset consists of the shapes obtained from three datasets, ABO, HSSD, and 3D Future. We gather a total of 354 shapes, manually annotating segmentation and mobility parameters. This dataset features more diverse and challenging object categories, geometric structures, and part arrangements. We also note that, as all the sources are static datasets, most of the shapes have missing interiors, making the distribution gap even larger. We note that ACD features more object categories, as well as a larger number of parts per object. Here we showcase ACD objects with interiors completed via our heuristic-based method. We start building FPN group on top of point group by improving the backbone. As the next step, we find that a simple MLP layer before point group heads, as used by prior work, is insufficient for our task. We designed the FPN feature adapter module, replacing this MLP, which leads to significant improvements. As the last step, we introduced topology-aware point cloud to mesh propagation procedure, resulting in more complete segmentation once mapped. Finally, we also add heads for motion parameters, creating FPN group mode. We find that baseline point cloud-based methods perform quite poorly, while our heuristic motion prediction is still somewhat capable of outputting reasonable motion parameters with incomplete segmentation. Our FPN group performs well on PM Openable, however still struggles to generalize to more complex shapes from ACD dataset. We can see that segmenting drawers is especially challenging due to the lack of interiors in ACD. See paper for more experiments with training on additional data that allow to reasonably improve performance on ACD. FPN group mode slightly underperforms in segmentation quality, as it also needs to optimize motion predictions. The produced articulations are reasonable, but are worse than our heuristic. We hypothesize that it would improve with more data available. Our simple interior completion heuristic can effectively generalize to a variety of base part and drawer geometries. Compared to other methods capable of outputting interiors, we respect the mesh geometry and generalize better, as we do not rely on retrieved meshes. Finally, we demonstrate that our pipeline is capable of automatically annotating shapes from existing static datasets. Here we present the results of applying our segmentation, motion prediction, and interior completion on ABO and 3D Future shapes not included in ACD. We hope our work helps to establish a unified framework and systematic benchmark for future work towards enabling large-scale interactive object datasets. Thanks for listening. Please refer to our paper for more implementation and evaluation details.